Good morning. Mais estudantes. Hello, good morning. One minute, give me a few minutes, I'll return soon. Okay, so let's think here. Okay, today is November 29, and we're going to cover waves, chapter 16. We're skipping chapter 15 and 14 for now. And first thing that you have to ask yourself, what's a wave? What's a wave? Okay, well, wave is an abstract, not just an abstract, but a genetic concept. Is an abstract, is a very powerful, let's put this here, is a very powerful abstract and genetic concept used in physics to explain certain real life phenomena. Okay? Types of waves. Types of waves. Okay, the most common type of wave is the one that propagates along a string. Okay? So think about you're holding a string and you move the string up and down. And what you're gonna see, you're going to see something that looks like that is propagating along that string. Okay? It's I'm quite sure that you folks have played with string. Let's see if we have a, here you go, here you go. I like this one here. This one's a good one. It can be a string, it can be a coil, okay? If you move this coil up and down, you're going to see something that gives you the impression that that's moving along this coil. In reality, it's not the matter that's moving in the coil or along the horizontal direction. What's actually moving along the coil in the horizontal direction is something else that we call a wave that has energy, by the way. A wave has energy. We can say that wave is energy propagating in a medium. We can put it this way, okay? What is a very powerful, abstract, and generic concept used in physics to explain certain real-life phenomenon. More specifically, a wave is energy that propagates along a medium, okay? Along it. And the most common type of wave, the one that propagates along a string or a coil. Another type of wave is a water waves. Sound is also a type of wave. And there's more. There's more. Now we have finally discovered, not finally discovered, but we have finally detected the existence of a very exotic type of wave that was predicted 100 years ago by Albert Einstein. 120 years ago by Albert Einstein, man. And this wave is called gravitational waves. That's another type of wave, but there are more. Matter waves, particles with mass, small particles, particles with mass, such as electrons and protons, such as electrons, protons, and others behave as a wave, What else do you have? Light. Light is a type of wave as well. Okay. And here in your book, we have some neat examples of waves. Here is a water waves. Okay, and waves happens whenever we disturb a medium. It's not water that's propagating here. Water is not moving along this direction. No. It's the energy that we generate in this medium that ends up propagating in the medium. The water doesn't move, in this case, the water doesn't move in the direction of propagation of the wave. The water moves in the direction perpendicular to the propagation of the wave. And here too is the same thing. The medium, which is this link, it moves up and down, whereas the wave itself propagates along the horizontal direction. Okay? Those two types of waves are a special type of wave that we call transverse wave. Okay? But then we also have another type of wave that we call longitudinal wave. Okay? You can move your link back and forth, right? Creating what we call a longitudinal wave. In this case, the sling, the matter, is not moving, each point of this medium is not moving from the left to the right. No, what's moving from the left to the right is the energy associated with the medium. What this medium is doing is just oscillating back and forth in the longitudinal direction. See the difference here? If here we have this wave oscillating longitudinally back and forth along the direction of propagation of the wave, here we have the medium oscillating up and down transversely at 90 degrees angle with respect to the direction of propagation of the wave. So to excite a wave, to create a wave, in order to create a wave, you must disturb the medium. Disturb the medium that the wave propagates on. The wave propagates on. That the energy propagates along. Okay? So if you disturb the medium, you're going to create a wave. It's just like the surface of a pond. You disturb the surface of the water with your finger, you are going to produce a wave. For instance, if you pluck your finger at the surface of what of a body of what of a body of water, you will disturb the water and create a wave that will propagate away from the point of disturbance. The water itself will move, will oscillate. Here you go, better. Will oscillate in the perpendicular direction. Okay? So here you go. Remember, there are two types of waves. Transversal waves and longitudinal waves. And you must remember which one is transversal, which one is longitudinal. Okay? I'm gonna tell you. You must remember that. There is no other way for you to, you have to memorize which one is transversal, which one is longitudinal. Okay, one, waves along a string, longitudinal waves, transversal waves. Here you go. Transversal waves. Waves along a string. Okay. Light waves. Light waves are also referred to as electromagnetic waves. We're going to study that in Physics 7, light waves or electromagnetic waves. Magnetic waves. Water waves. Okay. And let me put another one here. Earthquakes. Okay. There are waves associated with earthquakes. And by the way, in the case of earthquakes, some waves are longitudinal and some other waves are transversal. Okay. Some types of earthquake waves. Some types of waves associated with earthquakes are transversal. But then there are other type of waves associated with earthquake that are longitudinal as well. And longitudinal waves. Longitudinal waves along the string. Let's see. I also can put it waves along a coil that moves up and down. Okay. Here, longitudinal waves. Light waves are not longitudinal. Sound waves are longitudinal. And like I said, in this part here, you have to memorize that. Which one is transversal waves, which one is longitudinal waves. There's no other way, okay? And what else? a coil that is compressed or distended is a longitudinal, produces a longitudinal wave. Longitudinal earthquake, some types of earthquake waves associated with earthquakes. Here you go. So earthquake has both longitudinal and transversal waves. Let's take a look here at the internet. Those earthquake waves, they have a specific names, okay? Just to fill you in, here you go. Earthquake waves. Okay, types of earthquake waves. Okay, so here you go. They give names to those earthquake waves. Let's see, here you go. Do you see here, there is a type of wave that we call S waves. Those S waves are transversal waves. And then you have this other type of earthquake waves called P waves that are longitudinal waves. Okay? And they have some important characteristics. You can see one, their velocities are different. You can see that P waves are the first wave to hit their surface, whereas the S waves arrive after the P waves. Why is that? Because P waves are faster than the S waves. Okay, 1.7 times is lower than P waves. Okay, and P and S waves. There's another type of earthquake wave. Let's see if I can find it here for you. Love wave. They call it love waves. By the way, it's the waves that cause the most destruction. Okay, here you go. Here you go. That's the type of. This is it's also a transversal wave, but it's a transversal wave that's sideways, not in the vertical direction. Okay, it's the one that cause the most destruction. Love waves are the one that cause the most destruction. I once had a friend in my job there joking that love hurts, right? Yeah, love waves hurt. Love waves hurts the most. Is the one that causes the most destruction. Elastodynamic, okay? Not electrodynamic, but elasto for elastic. Love waves are horizontally polarized surface waves. Love wave is a result of interference of many shear waves. Oh, it's the result of the interference of many shear waves. We're going to study interference as well. Okay, so that's what I want to show here for earthquakes. Yeah. One more thing that you have to know, and I have some neat simulations here that I can show to you as well. We're going to study one-dimensional waves. Okay? And they can be treated mathematically. They can be treated mathematically, by the way. The most generic equation for an earthquake, for a wave, the most generic equation of a wave is the following. Okay, just like we write functions, a wave can be described by a function in x and a function in t. Okay? Remember, this is a dynamic wave. It's a dynamic type of phenomenon. The wave that we saw there is changes as time goes by, right? And what I'm going to do, I'm going to show you one simulation that I came up with for a wave. Let me get that, and I'm gonna pause momentarily. Remind me to start recording again, okay? Let's see here. Oh, no, this one here. Let's see. No, that's not this one. Is this one here? Summer and simulations. Yeah, let's see. Oscillations. Let's try those two here. Okay, good. I have it. I have them. I'm going to copy and paste those in your folder, in my folder, right? In the folder of the course, so I can access them more easily. Oh, see if I have simulation. It doesn't look like, yeah, I don't have simulations here. Unfortunately, I'll have to create a new folder. Today, see, today with computers, you can do this type of thing very easily. In our time, we couldn't do that easily whatsoever. Now let's go back recording. Pause recording. Oh, we are recording. I didn't notice that. Okay, good. So let's take a look here. Those simulations were made in Excel. Okay, let me show you right here. Enable content. And wait, let's see. Okay, here we go. Okay. So this type of wave is a periodic wave, it's a sine wave. And I'm going to, like I said, this wave is a function of the position. See that? The position here along this x-axis. And we see the amplitude of the wave. That's the amplitude. We call it the amplitude of the wave. And here, these waves, they are a function of time, okay? It's a function of time in terms of sine and cosine. If I go ahead and start changing the instant of time, you're going to see that there will be a change in the picture there of the wave. Oh, I don't want this one. I want another one. Okay, see there's a plus sign in there. I want the one that's the minus sign. No, I don't want that either. Let's see this one here. No, that's a standing wave. I don't want that. Let's take a look at the other one. Sound wave relativity. Well, you know what? Let's take a look at this one. Okay, and I'm gonna show you. I'm gonna put a negative sign here, so we don't have to struggle with this thing here. We're gonna play this movie, right? At time t equal to 0. That's how my wave looks like. At time t equal to 1 second, see what the wave did? It moved a little bit to the right. I'm going to undo the change. The wave is back. At 1 second, the wave moved a little bit to the right. Oh, you cannot see the waves? Let me see what you're seeing right now. Looks like I'm sharing. Let me stop sharing here. Let me try it again. What about now? Do you see it? Yeah. Yeah, okay. I do not know what happened here. Must have done something weird here. Okay, so let's do it again. At time t equal to 0. Thank you for warning me, Ridwan. Here you go. Oh, I want t equal to 0, right? Here you go. At instant t equal to 0, we have what we call here the crest of the wave. Here's the crest of wave, Here's the crest of the wave. Here's the crest of the wave. And here's the valley of the wave. Valley, valley, valley. And here's the node, 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 node. Okay? At time t equal to 0, the wave is at that position. At time t equal to 1 second, the wave moves a little bit to the right. 1 second later, just a little bit more. Another second later, just and so on. Okay? Now you have a picture of a transverse wave. In this specific case, this point of the wave, let's say the string, a string for instance, is moving up and down, just like that. Okay? And we do have, let's say, let's try this one here. Yeah, okay. Here's the same wave, okay? I want you to pay attention to this point right in here. This is, by the way, this is a realistic mathematical simulation of a wave, a realistic. You know, this is a point along the wave, your string, for instance. I made it larger so you can visualize it more easily. And this one too, I made it larger, one of the points along the string, right? So here you go, watch what happens to those points, right? Oh, it's too much. Okay, this wave is moving backwards. Okay, I don't want this wave. Let me go back to the other one. And then I'll make a change in this one. You got this one. Let's see, select data. Format data point must be this one here. Series options. Let's see. No, that's not what it is. Okay, I'll go back to that one. I don't want to deal with this thing. I will put a negative sign here. The negative sign here in this equation means the wave is propagating the forward direction. The positive sign means that the wave is propagating the backward direction, okay? So it's all the way around for waves. And we're gonna cover that. Here you go, 0. Let's try 0.5 now. Look where the wave is, right? Yeah, we gotta go back, we gotta go in smaller steps in this case. Let's try 0.2. Okay, now it's better, right? Now it gives you the impression, the illusion, right? 0 again, here you go. The illusion that the wave is propagating forwards. And I want you to follow this point here. This point doesn't move to the right or to the left. This point moves only up and down. The same thing for this point right in here. And I'm gonna do very small steps. 0.2, yeah. 0.4, 0.6, 0.8. Oh, 0.8. Right? 1. Okay? 1.2. See this point here, you can clearly see that this point stays along this line. Okay, 1.4, 1.6. Okay, it's not moving to the right or to the left, this big point here. The same thing applies to this one here. It just stays here in this line. 1.8, okay? 2. This is an example of a transversal wave. If I play a movie, you're going to see this thing flowing nicely to the right direction. 3.2 and so on. This type of wave is a special type of wave. How did you make the wave? Oh yeah. Yes, it's we're gonna cover that, how we make it. Here I'm just giving you a little feeling of how this thing, you know, you can take a look at this equation, okay? That's how I made this wave, okay? It's like plotting a sine wave, Camden. It's like plotting a sine wave. Here you go. You start, oh, don't do that. I did something stupid here. Oh, let's see here. Yeah, okay, now it's like plotting a sine wave, a sine function, okay? Camden, here you go. You start by doing that. Okay, so in this case, let's see here. I'm gonna do like that. Okay, it's like plotting a sine function. That's the first step. That's not difficult, right? Sine, and then you do something else. You start like that, and then you do something else. This something else I'm going to show you in the explanations of the wave that propagates. And now, here you go. Now we have a sine wave. This is not, we have a sine function. This is not a wave. This is just a sine function. And then what do? I do a small modification here to this argument of the sine function. So what I have here, you see that it's not a sine, it's a cosine, but it's the same thing, okay? See that I have, the B2 column right in here, but I have something which is inside the argument of the sine, right? But I have something else here that changes as time goes by. It's not that difficult to plot this sine wave, okay? But the first step is to plot the sine function. That's the first step. Make sense? And we're going to cover how I get there, how I got there, okay? What is difficult, Camden, is the sound wave. That was very difficult for me to figure out how to do that. It took me 4 hours to come up with this simulation, okay? That was kind of difficult. It's easier to see, to simulate a transversal wave, but then, I struggle a little bit to come up with this longitudinal wave. I'm gonna put it like, here you go. Let's go there. Now I have here one of the points of my longitudinal wave, which can be a molecule of air, okay, around you. And sound is a longitudinal wave. Sound that propagates in air is a longitudinal wave. So what you see right here is the model of sound propagating in a cylindrical container. Okay, so here you go. 0.2. Okay, it's too much. Let's see. Let's try 0.1 instead. I want to make sure that the steps are not too. Yeah, it looks like we have some good steps here. Yeah, we have some good steps here. Take a look here. Here is the region of compression, and here's the region of this tension, extended. The air molecules are very close to each other here, okay? And here the air molecules is very apart from each other. Here is like having the peak of the wave or the crest of the wave. And here is like having the valley of the wave, okay? So if you go 0.1 by 0.1, okay? You're going to see the wave moving to the left, right? So if I want to make the wave move to the right, I have to fix this sign here, just like I did for the other ones. Let's make the wave move to the right. Okay, just fix the sign from positive to negative. And now we are going to have the illusion that there is something moving to the right. Okay, 0, 0.1, 0.2, right? Follow these compressions here. The compression is moving to the right, but not the point. This specific point here that represents an air molecule. This air molecule is only oscillating along the direction of propagation of the wave. Okay? 0.4, 0.5, 0.6, 0.6 here. 0.6, 0.7, right? 0.8, 0.91. Okay? And the principle here is very similar to the other one. First, you do a trigonometric function. It can be either sine or cosine. Remember, right? Cosine is exactly as a sine. The only difference between a cosine and a sine is a 90 degrees phase in the argument of the function. So if I'm talking about a sine, I'm also referring to a cosine, okay? If I say, sine wave, it behaves exactly the same as a cosine wave. Okay, and I'm going to get, and I'm going to go back here to my notes. Okay, a wave, a wave is closely related to oscillations. Okay, we say that an oscillation generates what we call a periodic wave. Okay. We also say that the amplitude of oscillation coincides with the amplitude of a wave. Okay. We say the following. We say the following about a wave. One, an oscillation generates a periodic wave. Two, the amplitude of the oscillation, the numeric value of the amplitude of an oscillation coincides with the amplitude of a wave. So if you have a 10 centimeter amplitude for an oscillation, right? Here you go. You have a mass, right, oscillating with a spring back and forth. And let's say the amplitude is 10 centimeters. This oscillation can generate a wave of the same amplitude. Can generate a wave of same amplitude. What else? The frequency and period of an oscillation generates a wave of same period and frequency. So I should have written the amplitude just like that too, right? So you can put like that. The amplitude of an oscillation generates a wave of same amplitude, right? But then there are some things that a wave has that an oscillation does not have. Then there are some things that a wave has that an oscillation does not have. Okay, so what's that? One is the wavelength, I'm gonna say the speed. Okay? The only speed that your oscillation has is along the direction of oscillation. A wave has a speed that propagates in a direction perpendicular to the oscillation, right? I'm gonna say transversal speed. Transversal speed. And don't forget, transversal, it is transverse with respect to the oscillation. Okay? And one more thing that a wave has that an oscillation does not have is the wavelength. Okay. Waves has crests, valleys, and nodes. Okay. Let me show you each one of those properties. Like I said, here's a crest, here's a crest, here's a crest. Here's a valley, here's a valley. And here's a node, is a node, node, node. Nodes are positioned along a wave that coincide with the position of equilibrium. Okay, so crests. I'm gonna positions of largest amplitude, of largest positive amplitude. Okay, that's what it is. Valleys, position, and which position? Position of a point in the medium, okay, of largest positive amplitude. Position here, what about valley? Position of a point in the medium of most negative amplitude. And then we have nodes. Position of a point in the medium. Position of equilibrium of a point in the medium. Okay, those are things that an oscillation does not exhibit. Waves are something a little bit more complicated than oscillations, right? So we are doing this analogy between oscillations and waves, so you can understand better their relations. It's 10:02 right now. I'm gonna take attendance. Okay, so Gael is here, right? Hello, Gael. Gael Garcia. Okay, I'm gonna put a star here. This is what did I do here? I did something that I was not supposed to do. Let me see here. Every now and then I make this type of mistake. Okay, now I corrected. Good. Let's put aside. Lecture. Next, read one is here, right? Hello, thank you, read one. Ashley Zumo. Thank you, Ashley. Norberto Lopez. Thank you, Norberto. Vanessa Mena.
Here.
Thank you, Vanessa. Camden is here, right? Thank you, Camden. Marco Sanchez is here. Thank you, Sky.
Here.
Thank you, Sky. And Pacheco, Catherine Pacheco. Let's see, Catherine, I don't see her in my list. So let's sum it up. We have 7. Okay, and Gael didn't answer. Are you there, Gael? I don't hear from him. Okay, so let's take a little break now. Break from 10:05 a.m. to 10:20 a.m., right? And let's not forget, right, the lab report for lab 5. Report for lab 5 is due now. And today we are doing Lab 6, UCM1. So I'll see you in 15 minutes. Okay, Catherine, are you there? It looks like you just joined us, right? Catherine Pacheco? I see Catherine here. I'm gonna put a star in her name. Then once she gets back to the computer, I'll give her attendance, okay? So that's what we have for now for waves. And what I wanna do now is the lab 6. And let me see how is the group distribution right now, right? So let's see. Gael, you were originally with group 1, right, Gael? Which group are you now with? Are you there, Gael? Okay. I can't hear from Gael. Okay, group 2 has 1, 2. Ridwan and Ashley. Anybody else is in your group, Ridwan? And who else? Only you two? Okay. Group 3 has 3 students, right? And what about Marco Sanchez? Which group are you with, Marco? Is Marco there? Disappeared. Yeah, Annabelle. Well, Ashley is here, so you're in group 2 momentarily. Oh, I see, I see. Okay, so let me just put a note here. Inbox messages. Which inbox message? Did you send that to the Canvas inbox, Ridwan? Yeah, I never got any of your messages. Just let me know where do you send your messages, okay? So I can look there. Making groups and trying to exchange into between people now. You're okay. I'm talking to Ashley. Okay, okay, okay. Thank you. Okay, so let's see, Marco Daniel. So switch it to group. I'm gonna put it here. Switch it to group 2, right? Switch it to group 2. Group 2. And then let's see, what about Gael? Hey Gael, are you there? Let's ask Sky and Catherine. Hi Sky and Catherine. Was Gael in your group last time or
No, Gael wasn't in our group. It was someone else.
someone else? Do you remember who was that?
I don't remember, but I think that person dropped the class because we did try sending several messages to the person and didn't answer back at all.
Okay, okay. Okay, so let's wait for Gael Garcia to reply, and then we figure out what we're going to do with him. Okay, most likely I'm gonna put him in your group. Okay.
Okay, that's
So
fine.
okay, so group 3 has 3 people. So Michael Daniel is joining group 2, and now the only logical, right? The only logical place that Gael Garcia can be is gonna be in group 5. And let me get the lab on uniform circular motion. UCM1. For this lab, I came up with a video that I'm gonna show to you. But first, let's get the spreadsheet. Labs, lab report. No, not this one. Raw data. This one that I want. Okay, let's make sure everything is in the way it's supposed to be. One, two, three, four, five. Okay, let's take three. Just so it's kept in mind, Professor, that essentially means only group two, 3, and 5. Yeah, that's right. Let me go back here, the spreadsheet. Yeah, group 2, 3, and 5. That's right. Where do I get lab 5? What do you mean? What do I get? Where do I get lab 5? Ah, okay, I didn't upload that yet, Camden. Hang in there. I didn't upload that yet. I want to make sure everything is fine here before I release that to you. Okay, 2, 3, and 5. Thank you, Ridwan. 2, 3, and 5. And we're gonna get there to all physics. 2, 3, and 5. Okay, so now your spreadsheets are there, are posted in your group folder. You can go ahead and get it. And I'm gonna open my own spreadsheet here so I can walk you through how everything is done. Today's lab 6. Okay, okay. I can't find what I want here. Let me pause it momentarily. Resume recording. And now here.
Centripetal force experiment. Constant radius and variable mass. In this experiment, you will verify Newton's second law for an object undergoing uniform circular motion. You will change its mass while keeping its radius of rotation constant. This experiment has two parts. In the first part, you will measure the period of a rotating mass. In the second part, you will determine the force required to keep the mass under uniform circular motion.
Okay, so let's write it down. So you have that documented in my notes, okay? I will bold face it and center justify it. Okay, in this experiment has two parts. One, first, we will measure the period of rotation of a rotating mass. And two, then we will measure the force required to keep this mass rotating at a given radius. The experiment has two parts. First, we will measure the period of uniform circular motion. Okay, here goes better. Uniform circular motion of a rotating mass. And then we'll measure the force required to keep this mass rotating at a given radius. Okay. What else? What else we have to put it here? We will purpose verify Newton's second law of motion for an object who is constant mass. No, for an object with variable mass and constant radius undergoing uniform circular motion. That's the purpose of the experiment. And the experiment has two parts. Okay. So we are going to put also, equipment. The first one, going back here. Here you go. Here's the PowerPoint slide. The first experiment. Okay. First part of the experiment, determine the period of rotation of a mass. And the first thing, centripetal force apparatus. That's the first equipment that we have. The first, here goes, Senkos. Centripetal force apparatus. They sell those things out there. Let's take a look at the internet so you can see an actual picture of this device. Senkos. Centripetal force apparatus. Let's see, precision centripetal force apparatus. No, that's not the one. Ah, that's not the one. Okay, right in here, that's the one. That's the one that we use. It's not the exact, my video is not the exact reproduction of the picture, but it has the main elements. Okay, you have the support. You have, oops, what this guy is doing here. Let's see if I have a better picture for you to see it. I wanna, no, larger. No, I cannot get it larger. Ay, 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 ay. No. Save us. Centripetal force apparatus. I'm gonna save it in the download document. Download folder. No, I'll save it here instead. Labs. And I'll go there. And now I'll be able to zoom in and zoom out. Let's see here. Yeah, now I can do it. Okay, here's the base of the apparatus. And here's the low friction shaft. Okay. Shown right in here, the low friction rotating shaft. Right in here. So what we're going to do, we're going to put a crossbar. And the crossbar is this one right in here. The crossbar and the counterweight. I found that the experiment works better without the counterweight. I don't use this counterweight and I just clump this guy right here in my table. Okay, that's called a crossbar. Let's go back to our. Oh, what's going on here? No, that's not this one here I want. I want the one, other one. Okay, that's the rotating mass, right?
Its most important element is its low friction rotating shaft. In the first step, you will insert a crossbar near the top of the rotating shaft. To firmly secure the bar, its beveled regions must face upwards.
Crossbar. Pieces of this equipment. Centripetal force apparatus, crossbar with beveled regions.
Using the locking bolt, lock the bar along the longest of these regions.
Oh, locking bolt too, right?
The crossbar has a string from which you will suspend a rotating mass. A rotating mass is provided.
Okay, locking bolt. Locking bolt. Locking bolt? No, did I say locking bolt there? It's not supposed to be locking bolt. Let's see. Yeah, I wrote down locking bolt. It's something. It's not locking bolt. It's a locking screw, right? Should be a locking screw here. Locking screw and string. Crossbar, locking screw and a string. All those years and only now I figured that out. So here you go, crossbar with beveled regions, locking screw. Okay, and a string. Going back to my, here you go, rotating shaft, crossbar, and a string. Beveled regions crossbar must face up. Okay, lock the crossbar with a locking screw. Bolt is something else, right? And string. And what we're going to do next, we are going to get the rotating mass and we're going to measure the mass of the bob. The rotating mass is a bob. Okay. Going back right in here. And I want this video right in here. So play it.
The crossbar has a string from which you will suspend a rotating mass. A rotating mass is provided. This rotating mass is a bob. Measure its mass with a scale. Using the provided spreadsheet, log this mass with the right number of significant figures.
Okay, so next one. All the script here, equipment, Bob, which is the rotating mass. And then we're going to use a scale. So the scale that we use has a resolution of 0.01 grams, which is 0.12301 kilograms, 5 decimal places. Okay, if we go to our spreadsheet, go to the spreadsheet here. Everybody gotta have their spreadsheet open right now. Make sure you have your spreadsheet open right now. The mass of the Bob is logged right here at this spot. Okay, at this cell. Mass of the Bob, M Bob, in kilograms. Okay. Experiment has 2 parts. Okay, equipment. I'm writing the equipment. I'm gonna put it here, the procedure. Procedure. One. Get the centripetal force apparatus, right? 2. Insert the crossbar at the top of the rotating shaft of the low friction rotating shaft. Low friction rotating shaft. 3. Measure the mass of the Bob, which is the rotating mass. Then I'm gonna show you what is the theory behind that. Right in here, blow it up.
Suspend the Bob from the string of the crossbar. At the base of the apparatus, there is an indicator rod.
Okay. Suspend the hang the Bob. Hang the Bob from the end of the string. And we also have right in here, you go. I'm hanging the Bob from the end of the string. Right now, I didn't put my spring in there, but we're going to use it. We're going to use it very soon. Next. And then once we are done here, I'm gonna play this movie, okay, without any interruptions.
Slide the indicator rod until its tip coincides with the tip of the Bob.
See, we have this indicator rod that's very important. Is to be it's used as a reference to the tip of the Bob when we perform the experiment. Very important. Very simple way of keep track of the position of your Bob. Okay, so we go ahead and the components of the indicator rod of the apparatus, right? And then what do we do? You slide indicator rod to coincide with the horizontal position of the tip of the Bob. Rod and Bob, right? Rod and Bob. Tip of the rod, tip of the Bob. Tip of the rod to the tip of the Bob. Easy enough to remember, right?
Tip of the Bob to the tip of the rod. Using a ruler, Measure the radius of rotation of the bomb.
Okay. And let's take a look here. I don't expect you to memorize everything. It's lots of information to memorize it, but I want you at least to keep a general view of how this experiment is performed. Okay, measure radius of rotation of the bob with respect to the center of the rotating shaft. Keep in mind that I have done this experiment several times, okay? So because I have done it so many times, I just know it by heart. If you're doing that for the first time, it's not that easy. Measure radius of rotation of the bob with respect to the center of the rotating shaft. And then we have one more equipment here. Is that gonna be the ruler. Ruler with a resolution of 1 millimeter, which is 0.001 meters. Do we have, okay, yeah, we have another one here. My storyboard, right? Tip of, oh, here you go, indicator rod, move the indicator rod. I did all this storyboard before doing that simulation, that video that you're seeing, that you're watching right now. Okay, measure the radius, center of the shaft to the tip of the bob. And now we can go back to our spreadsheet and log the first radius right in here, cell G16. In the experiment, we are going to need also the G, acceleration of gravity, and you're going to see why. Okay, that's what we did right now. Going back to our video.
This measurement from the center of the rotating shaft to the tip of the mass bob. Log it in the spreadsheet. A spring is provided. Attach one end of the spring to the rotating shaft. Attach the other end of the spring to the mass bob. Pull the bob until its tip coincides with the tip of the indicator rod. Tip of the bob to the tip of the rod. While holding the bob, check if the spring is horizontal. If it is not, adjust the bob's height by either winding or unwinding the string attached to the crossbar. Remember, tip of the bob to the tip of the rod. Horizontal spring, vertical string.
Okay, so now one more thing here in our list. Okay, spring. I'm gonna put it equipment and materials, right? Spring. Attach spring to the bob. One end of the spring of the bob, attach one end of the spring to the bob and the other end to the rotating shaft. And here you go. We're gonna do that here too. Here you go, spring. Here you go. You gotta stretch it, make it the tip of the bob coincide with the tip of the rod, and make sure that the spring is horizontal and the string is vertical. Okay? If it's not, then you have to adjust the string, just like I illustrate here. One more thing that you do is that if this surface is raised against your table, you have to lower it down and clamp it with a C-clamp. So that's what we need, C-clamp. No. Lower the the base of the apparatus until it touches the table. Okay. Clamp it with a C-clamp. Clamp it to the table with a C-clamp. So we go another one here, spring, C-clamp.
Lower the apparatus with the adjustable bolts until the apparatus lower surface touches the table. Clamp the apparatus to the table with a C-clamp. Do not start the experiment until you align the bob, the rod, the spring, and the string. Also, ensure the apparatus is clamped to your table. This will prevent the apparatus from moving while you perform the experiment.
Okay, well, just by clamping the apparatus, I don't need to use that counterweight that you saw in that picture, okay?
Use your fingertips to rotate the shaft.
Okay, here you go, rotate the shaft.
Adjust the shaft's angular speed until the tip of the bob aligns with the tip of the rod. If the shaft rotates too slowly, the bob will pass between the indicator rod.
Here's the centrifugal force, right? If the bob rotates too slowly, its tip is not going to coincide with the tip of the rod.
But if the shaft
but if it's too fast, it's going to move away past the rod. So you must adjust the angular speed of this shaft with your fingertips, so you coincide, so you can match the tip of the bob to the tip of the rod.
Rotates too fast, the bob will move past the indicator rod. Practice this exercise a few times with the rotating shaft before you start. Once you learn how consistently align the bob with the rod, you can start the experiment. Using a timer, measure how long it takes for the bob to complete 20 revolutions. Adjust the rotating speed to align the bob with the rod. Then count down from 5, 4, 3, etc. At 0, start your timer and continue counting the revolutions until 20. Because of friction, you may need to propel the shaft with your fingertips every now and then. When you reach 20 rotations, stop the timer, read the period, and log this value into your spreadsheet.
Okay. So simple enough, right? That's how we measure the period of the bob. Let's take a look here. You know, the shaft to rotate. Okay, shaft is rotating. Shaft is rotating too slowly. Shaft is rotating too fast. So you have to adjust the speed of the shaft so the tip of the bob coincides with the tip of the rod, and count 20 rotations. Time for 20 rotations, and that's where we go right in here. Okay, this one, 20 rotations. Okay. At this moment, we are not adding any mass to the bob at all. For this reason, the mass that we have here is going to be exactly the same value that we have here in the spreadsheet. Remember, we're changing the mass of the bob and counting the period of rotation of this bob. And let's go to our, okay, what else do we have here? We're going to need a timer, right? Timer, let's not forget that our timer usually is 100th of a second. And the procedure. Put the bob to rotate and time how long it takes to complete 20 revolutions. 20 revolutions. Going back. right here.
As you count the number of rotations, ensure the tip of the bob remains aligned with the tip of the rod. Also, ensure the spring is horizontal and the string is vertical. If they are not, you may need to...
Oh, good idea, Ridwan. Let me do that so I can make it things simpler for you all, right? Yeah, here you go. I didn't have this idea. Ridwan came up with the idea of posting the link right here. I'll put that in my notes as well, okay? Link of the video so you can access. Let's see, Spring has 2 parts. Was posted. Its link is this one right here. And let's keep on playing the movie. Like I said, I will replay this movie in the entirety without any interruptions.
To either increase or decrease the angular rotation. If you still can't achieve alignment, you will need to stop the experiment and realign everything. Load a 20-gram slotted mass to a scale and determine its exact mass. Add this measurement to the bob's mass and log this result to your spreadsheet.
Okay, so next step and next material, right? Okay, it's slotted mass. 20-gram slotted mass. Okay. Measure the mass of your, it's not gonna be exactly 20 grams, but it's gonna be very close. Measure the mass of your 20 grams slotted mass with the scale and log this value in the spreadsheet. Okay, right thing here. Now we are at this step here. The radius is not changing. Measurement number 2. The radius is not changing. Why do I have 30 here? Okay, yeah, they didn't do 20, they did 30 here in this spreadsheet, okay? It doesn't have to be exactly 20. It can be 30, it can be some other measurements. The radius doesn't change. The radius doesn't change, but the mass change. We're adding mass to the experiment, to the bob, and the bob mass increases, right? So right here, and then we repeat for 20 rotations again. That's the idea of this part of the experiment.
Use the proper number of significant figures. Clamp the slotted mass to the top of the bob. The bob is a disc with a threaded hole. Use it to safely clamp the slotted mass to the bob. Pull the bob to the left until the tip of the bob aligns with the tip of the rod. Make sure the spring is horizontal and the string is vertical. If they are not, adjust the vertical position of the bob by winding or unwinding the string. Put the shaft to rotate and determine how long it takes for the bob to complete 20 revolutions.
Okay, we're just repeating what we did before.
The tip of the bob must be aligned with the tip of the rod. Compare this new measurement with the first one. Repeat the 4 previous procedures for 5 different slotted masses. 50 grams, 70 grams, 100 grams, 120 grams, and 150 grams. A total of 7 measurements.
Okay, so we did the first part, right? So go right in here. This slotted mass on the top of the scale. Here you go. Here the forces acting in your bob. Here's the force of the spring. Here's the force of the string. Here's the force of the weight of the mass. See that there is no horizontal component for those 2 forces here. So the only centripetal force applied to the mass is going to be that of the spring, okay? That's my free body diagram. That's my free body diagram. Okay, here's the added mass. We are clamping the 20 grams or 30 grams, depends how what mass you added there and put it to rotate again. Okay, put to rotate again. Here you go, everything, a fit for 5 additional masses, and everything put together for the first part of the experiment. Okay, everything put together for the first part of the experiment is right here, and here is the description of every little device, every little equipment in the rotating apparatus. So going back to my description right here, measure the mass of your 20 procedure, clamp the 20-gram slotted mass to the bob. Okay, put the bob, determine the period of 20 revolutions of the bob and the slotted mass. Okay, so going back right in here. That's with the 20 grams, and then that's the remaining. That's the remaining here. That's where we are right now. What is measurement and what is result? I'm going to illustrate you what's measurement and what is result. What you see here is a result. I'm gonna put it with a different color. Okay. Everything in yellow is a measurement. Everything in green, lower, light green. I'm gonna put a little bit darker here. I don't like this light green. Better. Dark green is a result. Why is a result? Because we are summing the mass of the bob with the mass of the slotted mass. Okay. We determine the period for one rotation, and we square the period of one rotation. There's a reason why we do that. I'm going to show you very soon. Those are results as well. Those are results as well. First part of the experiment. Let's play the movie. Okay, first part is over, and I'm gonna play the first part uninterrupted. So you...
Centripetal force experiment. Constant radius and variable mass. In this experiment, you will verify Newton's second law for an object undergoing uniform circular motion. You will change its mass while keeping its radius of rotation constant. This experiment has two parts. In the first part, you will measure the period of a rotating mass. In the second part, you will determine the force required to keep the mass under uniform circular motion. Its most important element is its low friction rotating shaft. In the first step, you will insert a crossbar near the top of the rotating shaft. To firmly secure the bar, its beveled regions must face upwards. Using the locking bolt, lock the bar along the longest of these regions. The crossbar has a string from which you will suspend a rotating mass. A rotating mass is provided. This rotating mass is a bomb. Measure its mass with a scale. Using the provided spreadsheet, log this mass with the right number of significant figures. Suspend the bob from the string of the crossbar. At the base of the apparatus, there is an indicator rod. Slide the indicator rod until its tip coincides with the tip of the bob. Tip of the bob to the tip of the rod. Using a ruler, measure the radius of rotation of the bob. Take this measurement from the center of the rotating shaft to the tip of the mass bob. Log it in the spreadsheet. A spring is provided. Attach one end of the spring to the rotating shaft. Attach the other end of the spring to the mass bob. Pull the bob until its tip coincides with the tip of the indicator rod. Tip of the bob to the tip of the rod. While holding the bob, check if the spring is horizontal. If it is not, adjust the bob's height by either winding or unwinding the string attached to the crossbar. Remember, tip of the bob to the tip of the rod. Horizontal spring, vertical string. Lower the apparatus with the adjustable bolts until the apparatus lower surface touches the table. Clamp the apparatus to the table with a C-clamp. Do not start the experiment until you align the bob, the rod, the spring and the string. Also, ensure the apparatus is clamped to your table. This will prevent the apparatus from moving while you perform the experiment. Use your fingertips to rotate the shaft. Adjust the shaft's angular speed until the tip of the bob aligns with the tip of the rod. If the shaft rotates too slowly, the bob will pass between the indicator rod and the rotating shaft. If the shaft rotates too fast, the bob will move past the indicator rod. Practice this exercise a few times with the rotating shaft before you start. Once you learn how consistently align the bob with the rod, you can start the experiment. Using a timer, measure how long it takes for the bob to complete 20 revolutions. Adjust the rotating speed to align the bob with the rod. Then count down from 5, 4, 3, etc. At 0, start your timer and continue counting the revolutions until 20. Because of friction, you may need to propel the shaft with your fingertips every now and then. When you reach 20 rotations, stop the timer, read the period and log this value into your spreadsheet. As you count the number of rotations, ensure the tip of the bob remains aligned with the tip of the rod. Also, ensure the spring is horizontal and the string is vertical. If they are not, you may need to either increase or decrease the angular rotation. If you still can't achieve alignment, you will need to stop the experiment and realign everything. Load a 20-gram slotted mass to a scale and determine its exact mass. Add this measurement to the bob's mass and log this result to your spreadsheet. Use the proper number of significant figures. Clamp the slotted mass to the top of the bob. The bob is a disc with a threaded hole. Use it to safely clamp the slotted mass to the bob. Hold the bob to the left until the tip of the bob aligns with the tip of the rod. Make sure the spring is horizontal and the string is vertical. If they are not, adjust the vertical position of the bob by winding or unwinding the string. Put the shaft to rotate and determine how long it takes for the bob to complete 20 revolutions. As before, the tip of the bob must be aligned with the tip of the rod. Compare this new measurement with the first one. Repeat the 4 previous procedures for 5 different slotted masses. 50 grams, 70 grams, 100 grams, 120 grams, and 150 grams. A total of 7 measurements. You will now measure the force the spring applies to the bob.
Okay, now is the second part of the experiment. Before the spring applies to the bob. Remember, we did the first part, right? First part ends right in here. First part was just, we did the first part just to determine the period of rotation of the bob. And now we are going to use a special procedure to determine the force that the spring applies to the bob, which is going to be the centripetal force. Going back here.
This force is equal to the centrifugal force. This part can be performed without a C-clamp. Using a 1 meter long string, attach it to the left side of the mass bob. Pass the other end of string 2 through the pulley. Attach a mass hanger to the other end of the string.
Okay.
Load several slotted masses to the mass hanger. Load these.
Okay, so what we have here, we have 1 meter long string, part of the material, part of the, attach the 1 meter long string to the bob. Attach one end, right? to the bob. Attach the other end to a mass hanger. Okay, so going back here to my equipment and materials, 1 meter long string, 50 grams mass hanger. Okay, and several slotted masses. What we're going to do here, we're going to use add as many slotted masses to the hanger until the tip of the bob coincides with the tip of the rod. Isn't that a simple procedure? Okay, to find out that force right in here. So, okay, here's the free body diagram, right? The mass that were added. Notice that as we add the masses to the rod, you know, those added masses doesn't interfere with the centripetal force, with the force that the spring is applying. Okay, there's no component, even though we are adding masses, okay, the centripetal force remains the same. Centripetal force remains the same because the radius remains the same. The centripetal force remains the same because this mass here, this component, the vertical component of the force, has no horizontal component whatsoever. Okay, and here's the second part of the experiment. We go, the string, the meter-long string, pass the strings through the pulley, add a mass hanger. And the mass hanger is not heavy enough to stretch the spring. That's why we have to add slotted masses to this mass hanger. Once we have the tip of the rod coinciding with the tip of the rod, of the bob, this much mass here will have a weight that's going to be equal to the force that the spring is applying. Okay, so here you go. Force, right, that the mass hanger is applying to the bob, force that the spring is applying to the bob. Okay, so this much mass coincides with this much mass produces a weight that coincides with the force that the spring applies to the bob. Okay, mass hanger with a slotted mass on the scale. So that's what we have right in here. Add as many slotted mass to the hanger until the tip of the bob coincides with the tip of the rod. Measure the mass of the mass of the hanger with the slotted masses. Its weight, the weight of the set, is equal to the force the spring applies to the bob. Okay, and that's what we do right in here. Okay, the mass hangers. The way, and those are experimental measurements that I put with yellow color. What you see right in here is the velocity of the masses, the velocity of the bob, okay, which I am going to put with a green color. What you see right in here is this mass that's hanging there times the acceleration of gravity, or the force that the spring is applying to to the bob. And here is a theoretical value as well. I'm going to show you how we get this theoretical value. And everything else here are results. Okay, let's see, do we have anything else? Right in here, yeah. So we're done with this experiment. Let's finish with the video.
Masses until the tip of the bob aligns with tip of the rod. Also, check if the spring is horizontal and the string is vertical. Using a scale, measure the net hanging mass. Mass hanger plus slotted mass. Log this measured value in your spreadsheet. Add the 20 grams slotted mass to the top of the bob and repeat the 4 previous steps. Repeat this step for the remaining slotted masses. 50, 70, 100, 120, and 150 grams. You completed the experimental part. Now perform your data analysis and determine if your experimental results are close to the theoretical ones.
Okay, that's the logo of my business. And let's stop here. So what else do you have to know? Once you're done with the experiment, you're going to need to plot the mass in the y-axis and t-square in the x-axis. Why do we do that? There's a reason why we do that, okay? Let me show you why, just by coming up with the derivation of the equations that we have. Let's see here. Oh, this one right here. Recall that the centripetal force is equal to mass v squared over radius of rotation. Let's put big M, okay? Let's put big M here. But let's not forget that since it's uniform circular motion, this V is going to be 2 pi r over period of rotation, okay? Which ends up becoming M 4 pi square r square over t square, okay? And then we got rid of the square outside the parentheses. R cancels out with R. Okay. And then what else do we have? We have the following. Remember that I told you that the centripetal force doesn't change, right? So we pass the t squared to the other side. All of that is a constant, okay? And let's not forget that the centripetal force also is equal to the mass hanger times G, okay? This is variable, this is variable. This is variable, this is variable. Everything else is a constant. If we are plotting M in the y-axis and t squared in the x-axis, we must divide that by 4 pi square r. Okay, like that. Big M, like that. Y-axis, x-axis. The slope, that's the slope. Okay? That's the slope right in here. And now let's go ahead, plot, plot M along the y-axis and t square along the x-axis. And see if you get a straight line. I'll do that. M and T. Okay, this one is going to be a little bit tricky because I put the parameters that are going to go along the y-axis in the left side, right? And then make sure you get the right plot. Here you go, see? I say straight line. But don't forget, what I have right now is m along the x-axis and t squared along the y-axis. So what I need you to do is to swap the axis. And to invert the axis. How do we do that? There's a very easy way to do that. Okay, we do the following. Click one of the data points, right click it, and then what do you do? Select data. Follow that with me, please. Let make sure everybody is following, right? So at this point in time, 8. Download spreadsheet. Let's see. Gael, are you there, Gael? Gael Garcia? I don't hear from you. Okay, I'm gonna press star right here. Ridwan, are you there? Hello, okay. Do you have the spreadsheet there? Did you download the spreadsheet? Yes? Yes, okay. So I wanna know, now I want you to plot the graph, right? Plot graph. I wanna make sure everybody plot, oh, not yet, it's lost. What do you mean it's lost? The spreadsheet? The link, I have a lot of tabs open right now. Okay, don't forget, you have to download the spreadsheet to your hard drive, right? You have to download the spreadsheet. Okay, so I'm gonna say that you're working on that. Ashley, are you there, Ashley? Oh my goodness. Oh gosh, too much. Don't do that. Close most of the tabs or start from scratch, right? Did you download the spreadsheet, Ashley? Okay, good. Did you plot the graph? Yes, not yet. Okay, so I'm gonna put that you're working. You wanna ask something, Camden?
I download the spreadsheet, but I'm not sure if I download the right one. Table 6.1, right? Raw data.
Let me check. Yeah, table 606162. Your group
Okay.
number, did you get it right or not?
Yes, I think I got the group number 3.
Okay.
Lab data.
And
But I have a question.
yeah.
How do I plot the data? Like, I don't know which one I need to select.
Okay,
Like,
so here goes. It's written there in your spreadsheet. Let's see. Let me close this one first. Okay, so here you go. Is mass and t squared. That's the first step. Okay. Mass and t squared. And then you have to invert the axis. I'll show you all how to invert the axis. First, get it plotted, and then I'll show you all how to invert the axis, okay?
Okay, so mass and t squared, right?
Yeah, mass and t squared. You want m in the y-axis and t squared in the x-axis. When you do this plot, you're going to end up with the m in the x-axis and the t squared in the y-axis. And I'll show you how to invert the axis.
Do we need the regression as well?
Oh, yes.
Oh.
Yes.
All right. Thank you so much.
So I'm going to put that you're working, and let's see. Norberto.
I just did it.
You did it? Okay, good.
Yeah.
So, but you didn't finish yet. You still have to invert the axis, right?
What do you mean invert?
I'll get to there. Let make sure everybody plots, get to the point where you are, and then I'll tell you how to invert the axis, okay?
Okay, thank you, Professor.
Okay. Norberto, are you there? Hello, Norberto. Okay, you was able, okay, good. So you graphed, that's good. And then come then, no, Vanessa now. Oh, really? Okay, okay. So I'll show you all. Let's see, Vanessa, are you there?
Yeah.
Okay, good. Did you download the graph, the spreadsheet?
Yeah, I downloaded it and graphed it.
You graphed you, right? Now you have to invert, right?
Yeah.
Okay, did you manage to do that yet?
No.
Okay, I'll show you how to do that, or you can interface with Norberto, see how he did that, okay? So let's see, Marco Sanchez, are you there, Marco? Okay, graphed, okay, good. Did you invert the axis, Marco? No, okay. So Sky, did you download the spreadsheet and you plot the graph? Sky is not here. Okay, Sky left. Okay, looks like she left. Okay, left. Now, next one is Catherine. Catherine, are you there? Hello, Catherine. Okay, Catherine doesn't answer. I'll put a star here. Okay, now I'll show you how to invert the graph. I have my graph right in here. Okay, write it down, write it down. Click one of the data points. Okay, right click one of the data points. Select data. Okay.
Professor, what did you say?
Okay, we're going to invert the axis. Okay,
But
you want me to do it again?
select data? What's that?
Yeah, click one of the data points. Here you go. Click one of the data points. All the data points are highlighted.
And then?
Okay, right click. When you right click, you have this drop down menu. Select data. When you have you select data, this window comes along, and highlight the cities and edit.
Okay.
Edit it. Okay. Look here. Series X values. Series X values is I column, right? The I column is the mass. You don't want in the X value. You want the mass in the Y values. Okay. So see that L, series Y axis, L. L is what? Is the T square. So you don't want in the Y value, you want in the X value. So you're gonna have to exchange the I by the L. Let's see if I can get that.
So type
yeah.
L in
exchange I for L and L for I. L for I. When I do that, the graphs are inverted.
Can you show me one more time?
Okay, let's do that again.
No, I mean the typing L part, because like when I select the L alphabet L, it would just like generate a bunch of other gibberish words.
Yeah, you gotta be careful with that, right? You gotta be careful how you do that. Undo everything that you do. Click cancel there in that window of yours. Okay, your graph is preserved, right? Your graph is in the way it was before, right? So let's do it again. Click one data point, right click that data point, select data, highlight series, edit. Put your cursor next to L. Back, but not next to L, next, in your case, gonna be next to I, right? Give back and type L there. you know, here you go, back and type, you know, L there. And then you do the same for the other one. You cannot use the cursor. See, if you use the cursor, you get all this gibberish that you mentioned. See that?
When
So
I do, okay, so when I try to modify the thing and hit okay, it will tell me that the reference is not valid. References for
okay,
title.
maybe because you mistype it. Maybe
Oh,
because
really?
you mistyped. Yeah, maybe because you mistyped it. Do it again. Highlight, edit, click next to the letter. Don't use the arrows in your keyboard. Use the back key. If you use the arrow, you're gonna get all that gibberish that you got it. And then you type L, right? Put your mouse next to L again, back, L, right? And you do the same with the other one in the Y values. Okay.
It wouldn't change somehow. Let me see.
Where you get it? Oh, it does change mine here.
It would just tell me that it's invalid comment or something like
Are
that.
you using a Mac or a Windows?
Oh, Windows.
Okay. Let me check with the other students. They have the same problem. Is anybody else having the same problem? I don't have this problem here with my computer. You got a workaround? Okay. Okay, so you did differently from me. Another way that you can do. Okay. Another, yeah, you worked for Marcos. Okay. Okay, if you're having any problems, you can do the following. There's another way. There's a workaround, just like Reed once said, right? If you, I do not know if the workaround, mine workaround is the same as Reed, but you can do the following. You can copy M, okay? Copy and place it right here. But then when you paste, you're going to, it's going to be this special paste, 1, 2, 3. Okay? I don't think it's case sensitive. No, it's not case sensitive, Michael. Okay, that's
Professor,
all.
if you let me share my screen for a second, I can show you how I can show how I did the workaround.
Okay, so let me see here. Let's see. I gotta stop sharing my screen. But let me finish. Let me finish, and then I'll let you in. Okay. So let's see. You can copy the T square, right? That would be another workaround. And you paste the actual numbers. Don't use the regular paste. Use the paste 1, 2, 3. Okay. And you get the space 1, 2, 3 by right clicking. Okay. And now this one is gonna be the T square. This one is going to be M. And now when you do this plotting, then you're going to get the right, okay, the right axis. Let me see. I'm going to stop sharing here. I'm going to go ahead. Is that Norberto, right?
But which one do I need to select first?
Let's see.
No, it's read one, right? Read one. Okay. Okay.
So
let's see what's workaround of read one.
We'll start off by clicking on the dot, like you said, select data, edit. And when we come up here, what we can just do instead, we'll copy the first one, put it here in the series name temporarily.
Good.
And we'll just copy this one over.
Yeah, and paste.
There.
Oh,
and then we're going to cut this one
better.
so it's no longer in the series name. Then paste, and then you can hit OK.
Okay, don't cancel. All right, don't cancel.
Well, I already did it, so that's why I said cancel. But yeah.
Okay, got it. Okay, that's a good workaround. You copy those lines, put in that temporary cell, right? And then you do the rest, right?
Yep.
So there is more than one way of doing that. We found out 3 different ways, right?
Yes.
Okay. Did it work, Camden?
Oh, I'm about to try right now. Let me try.
Okay. Let's see. We're running out of time, right? We have only 15 minutes.
I stopped sharing so you could share your
works.
screen again,
Ah,
Professor.
okay, good. Let
It
me
works.
share my
Thank you so much.
screen. That was nice thing about computers. They always build enough stuff in there so you can do the same thing in different ways. Okay, so let's see how everybody else is doing there. Right, so at this point in time, let's see. I want to see if you switch it. I'm going to assume that everybody plot in the wrong way, right? In the incorrect way, and then you tell me that you invert if you inverted axis. Gael, are you there again, Gael? Let's see if Gael is around. I don't see Gael here. Okay, next. Ridwan. Okay, you inverted, right, Ridwan? Ashley, did you manage to invert the axis? Hello, Ashley. I don't hear from Ashley. I put a star here for her. Norberto, did you invert the axis, Norberto? Yes, okay. Ashley is still working on that. That's good. Thank you, Ashley. Vanessa, did you invert the axis? Okay, I'm gonna put a star here for Ashley. Ashley, no, for Vanessa. Marco Sanchez, did you manage to invert the axis? Manage, right? You did, because you said that you worked it before. Yes, okay, good. Next is, oh, no, Camden. Oh, okay, Camden did it, right? You managed to do that, right, Camden?
Yes, it worked.
Okay, good.
Thank you so much.
Okay, welcome. Sky. Sky is not here. Oh, well. Next is Catherine. Hey, Catherine, are you there?
Yes.
Okay.
I'm working on it.
You're working? But did you plot the first graph with the axis inverted? I'm gonna say that you did, okay? Okay, now that Catherine is here, I can adjust the attendance. Ten minutes. 10 minutes to go. Okay, so what you have to do next is just, trend line, display function R square, right? And what else do? You get this slope. This is slope here, huh? You copy right in here. 1.31, what? 1.3117. Okay, and look what we get. We get only, for my case, we get only 2% difference. You get only 2% for my case, right? I do not know about you, but so I'm going to undo everything that I did in the spreadsheet. Uh-oh. Let's see. Undo everything that I did in the spreadsheet and not bad. I'm going to raw data right in here. 6. There you go. Sample, yeah, and then I'll work this one here and preserve the other one. Let's see, Professor, how did got for the axis title again? Was it something like, yes, that's right. Oh, wait a minute. M for kilogram, and the other one is T square, right? M parenthesis kilogram. The unit is always placed between parentheses. M space, right? Parenthesis kilogram. And then you do the same for T square. T square, parenthesis, and then the unit there inside. We're running out of time. 8 more minutes to go.
Professor, I have a question.
Yeah.
It's about the plotting data.
Yeah.
What if you just select the this T square first and then plot and then select the M as the second one, then plot
Doesn't
it.
work.
Oh,
Doesn't
okay.
work.
Very one. Okay.
I tried that too. When I was trying to figure that out, I was trying everything, and then I just came to the realization that it doesn't matter, whatever is to the left is going to end up in the x-axis. Whatever is to the right ends up in the y-axis. And then we have to go through that trouble that
So time is
we
always
went.
going to be the x-axis, right? No.
What's that?
Time is going to be always axis, T squared.
Yeah, whatever is to the left ends up in the x-axis.
Oh, okay.
X-axis. Yeah, whatever is to the left ends up in the x-axis.
Okay. All right.
Unfortunately, I wish Microsoft would do things simpler. Just like you said, I think it's a great idea. If the first one you highlighted, right, you make it the x-axis. The second one you highlight, you make it the y-axis.
Right.
But for some reason they didn't implement that.
Thank you.
What is supposed to be negative, Marco? D? Delta. It can be negative, depending how I put the formula. Let me see. Are you talking about this one? Yeah, this one can be negative because the way I put the formula, see here? It can be either positive or negative. Yeah, but the other delta, no. The other delta I wrote down, I put an ABS here for absolute. But it's okay to be negative. It's okay to be negative. Yeah. See, I use different formulas. This one, I just got the absolute value. This one, I didn't bother to keep the absolute value in there. It's okay. You can have a different negative percentage difference. Then you have to interpret, right, what means a negative percent difference, right? Anything else? 11:55. So the biggest struggle here was to invert the axis. We discovered 3 different ways, right, of inverting the axis. Let's do it again. Here you go. T square M, insert chart. Here you go. Click, right click, select data, series edit. Yeah, get this guy here, copy it and paste it momentarily. And then get this one here. copy it, or even cut it if you want, and paste on this lot of the x-axis, the x value. And now you cut this one and paste it. And then you get the proper inversion. Like I said, I wish Microsoft would do something simpler than that, but you know, if you go working for Bill Gates, just tell him, tell him about that. Click that arrow to the right, you can select the raw data. You mean, let's see, arrow to the right, this one here? I tried to do that too. Are you talking about those two arrows here, Norberto? In edit, let's see. I don't see arrows here. I don't see any arrows here. There is a map arrow. Do you see? Oh, yeah, I see. Let me see. Let's see. I didn't know that. Ah, no. It doesn't do anything. See that? It just up arrow. See that? It just collapsed the window. Let's see. Select the data. Oh, I see what you mean. Let me see here. Select the data. Yeah, okay. And then you copy, right? Select the data and then you copy it. Okay, that's one way too.
Professor, I have a question.
Yeah.
Where do I submit my extra credit files?
Okay, did you finish everything?
I only have one more files
Okay.
to go,
Okay.
but
Okay, let us talk about that on Monday during my office hours. Okay. And then I'll not call. Let me go back to Norberto here. Okay. What do you mean not copy Norberto? What do you want me to do? Here you go. Arrow up, right? And then what do we do? Select the cells you want in the axis, but where? I have just this window here. See that? Are you talking about the table? In the axis or in the table? Oh, cool. Yeah, that's another way. Good point. But then you gotta make sure that you do not have okay, you do not, yeah, I got it. I got what you mean. Yeah. Okay, but you gotta make sure that you do not have any thing blocking your table, right? You gotta make sure that, let's see. Yeah, okay, so here you go. Make sure it's not blocking your table. And now let's do it. Select graph, edit, and this one. This one should be what? This one should be the x values, right? The x values should be, yeah, t squared, right? And now the y values should be m. Okay, okay. We found 4 different ways of doing the same thing. This one is far more convenient than the others, right? Far more convenient than the others. Good point. Yeah. So what I'm going to do, Camden, I'm going to give you a link in Google Drive for you to upload the files, okay? That's what I'm going to do.
okay.
We will set that up on Monday.
Okay.
I will set that up on Monday for you. Yeah.
So you said this is going towards 15 or 10%? I forgot how much
What
it's
did you
going
say?
to. I forgot how much it's going to worth for the
Just 5%. Just 5%.
oh 5%. Oh, okay.
Let's see what you did there. Okay, it's 11:01, right? 12:01 right now, right? So we can stop here. Don't forget this lab report is due next week, Wednesday. The report for this lab is due next Wednesday. Next Wednesday is what? Is December 6th. December 6th, 23. Okay. So I see you Monday.
I have some questions about homework. Am I allowed to ask you?
Yeah, let's do that on Monday. That's my office hours.
Monday? Oh, okay.
Yeah, I have something else going on right now. So,
Okay.
so if we do that on Monday, and I'll help you out with the homework.
Okay. Thank you
Okay.
so much, Professor.
Oh,
Have a good one.
welcome. Bye-bye.
Oh, Professor, when you were asking about the graphs being inverted, you put a star next to my name, but I had replied in the chat that I got it inverted.
Let me see. I think I corrected that, right? Let's see. This one here, right here.
No, for
No, it's
Vanessa.
Vanessa. Vanessa. Okay, so you put Y, right? Yeah, okay, I
Yeah.
forgot to correct that. Okay, thank you.
Okay, that's it. Have a great rest of your day, Professor.
You too. Bye-bye.
Bye.
Tá quente lá fora?